In this video, we're going to learn how to draw organic structures. This is based on what we learned about the Lewis structures, lone pairs, and bonding pairs, and all those things. In this video, we're going to just learn how we're going to draw organic molecules or organic structures as we are doing all kinds of organic work on paper. Before we actually get into the different type of drawings of organic molecules, I'd like to make sure we're on the same page about a couple of terms. One is that there are two types of atoms usually we say in organic molecules. The first type is carbon and the hydrogens. We say these two atoms are basically the backbone of most of the organic molecules. As you can see, most organic molecules contains carbons and hydrogens like the feathers around the carbon backbones. And basically all of the rest of atoms, we call them header atoms, which covers basically any other atoms other than carbon hydrogens, including oxygen, nitrogen, any of the halogens, or even metals. So we basically separate the carbon hydrogens from the rest of the elements in this universe. So for the ease of discussion in the future, when we say header atoms, you know what we're talking about. We're just talking about anything that's not carbon hydrogen. Usually when we draw the organic molecules, or you would believe how we draw organic molecules would be like what we see on the top. We basically draw out all of the atoms and all of the bonds, and then just like how we draw the Lewis structures. We call them Kekule structures. Now there's only one little difference between Kekule structures and what we normally draw as Lewis structures, is that we don't really show the lone pairs. But at the same time, we assume that we all understand that all of the atoms, except the hydrogens, fulfill the octet rule, also called the tetravalent rule. So for example, this carbon has 4 bonds here, so it doesn't have any lone pairs. It's neutral carbon. If you want to see more detail about this kind of information, you can review the first 2 videos in this chapter. The bromine here, you can see, has only 1 bond. Now, even though without showing, we would assume everybody understands that there are actually 3 lone pairs around this bromine. Now, similar situation you can find around this oxygen, even though it only shows 2 bonds here, but there are 2 invisible or hidden lone pairs around this oxygen, complete the tetravalent or so-called octet structure of this carbon. And same thing, this oxygen would also have 2 lone pairs, which is not shown here, but we know they are there. Now, other than drawing all of the atoms or element symbols with bonds, we can actually draw something so-called condensed structures. The condensed structure you can see is that we omit all of the bonds or dashed lines. We bring all of the element symbol together to form this kind of look like a chemical formula, but actually they're not like the formula we normally would do. We're actually trying to show some structure information in this kind of condensed structures. You can see CH3 as a group of atoms next to the bromine. In the second example, you can see there are 2 CH3 groups atoms connected by an oxygen in the center. You can see this acetic acid example, there is a CH binding along with a COO binding next to a hydrogen. So how do we really convert this Kekule structure into condensed structure? There are a few rules we can basically follow. In the future, you can, after you practice enough, you don't really have to memorize, you basically just know how to do this kind of thing. For example, all of the atoms are going to be drawn without the bond dash lines. The atoms will basically draw next to each other, but you only draw next to the atom they are actually directly bonded to. You can use parentheses to use around similar groups bonded to the same atom, which we're going to see some examples. And again, we don't really show the lone pairs. So, for example, this is the butane with 4 carbons in the center, and you can see all of the hydrogens are attached to each carbon. Each carbon here basically shows 4 bonds like what we showed earlier in the other video, full bond pattern. Okay. Now, if we really draw the condensed structure, you would highlight that CH3 as the first group atoms, and then followed by CH2, CH2, two CH2s, and then one last CH3 at the end, terminal CH3s. Now, this is perfectly fine, but you can also further simplify this into CH3, parentheses CH2, another 2 outside the parentheses CH3. Now, you can see in the center, CH2, parentheses 2, representing 2 repeating CH2s. Now, either way will be perfectly fine, but you should be able to tell what this parentheses 2 means. In the bottom structure, you can see that there are actually 4 carbons, and each carbon would have enough hydrogens to complete its full bond. And you can see in this structure, there's a carbon in the center, and attached to this carbon, there are 3 CH3 carbons, or CH3 groups. And then this carbon also attached to another hydrogen. So in the condensed structure, you can see there's a CH3, parenthesis 3, next to a CH. Now this CH, let me highlight this. This CH is basically the CH here. Let's look at a few more examples of a condensed structure. CH3, CH2, CH, and then this on the CH, there's another CH3 attached. And then on the other side, you have CH2, CH3. So the condensed structure will look like CH3, CH2, CH, CH2, CH3, and then on the CH there will be another CH3. Now the other way you can show this side branch CH3 is that to put CH3, CH2, which is the same as, as the CH2, CH2, and the same as CH2, CH3, but merge the CH3 into parentheses CH3, representing the CH3 is attached to the carbon in front of it. It's not directly attached to the carbon next to it. In the next structure, you can see there's a CH3, and there's a CH, there's a CH, and there's another CH3. So the condensed structure will look like CH3, CH, CH, CH3. There's one thing I do want to highlight, that is that when you have a double bond, it has to be shown in even condensed structure. You can't just put 2 CH together. When you put 2 CH, CH, or any carbons together, you would assume they're only connected by a single bond. So when you have a double bond, you do have to show or specify them in the condensed structure. In the next structure, we do have a header atom, which is oxygen. And you can see there's CH3, another CH3. So 2 CH3s attached to the CH. So what's shown in condensed structure is 2 CH3s in the parentheses, and then followed by CH. Let me highlight in different colors so you can see the CH is actually this CH is actually this CH. And then next to the CH is bonded to CH2, which is this CH2, next to OH at the end. So you can see that in the condensed structure, you show the header atoms, but with no lone pairs next to oxygen. In the skeletal structure of the very last one, you can see in the first group, instead of a CH3, the both hydrogens are replaced with the chlorines. The way you're going to show this kind of thing is going to be Cl2CH, which if you imagine these are not Cls, they were just hydrogens, this would be just CH3. But now since there are 2 chlorines, so you have to show Cl2CH. And next, it followed by 2 CH2s, CH2, so you will have CH2 and CH2. And then CH2 is attached to oxygen. You can see the oxygen with no lone pairs. and oxygen attached to the carbon with no hydrogen. So you can see this carbon here. But this carbon is attached to CH3, 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 3 CH3s. So it can be represented by CH3 with a 3 outside the parentheses. I guess it's not hard to see that the CH2, two of CH2s can be further combined, merged into a CH2 parentheses 2. So you can see the first group and then CH2s, 2 of them, oxygen, carbon, and then 3 CH3s. When you have a CO double bond, sometimes it's not as easy, can be easily seen. You have to determine, show that the number of hydrogens on the carbon can help you to determine whether it's a double bond or single bond. For example, CH3CHO, if you believe that this is just going to be CH3, which is relatively easier, carbon with 3 hydrogens, bound to a carbon, and carbon bound to oxygen, oxygen bound to a hydrogen. You can see that with no further hydrogens available, this carbon would not be stable enough to exist. The actual structure is actually a CO double bond with hydrogen. That's usually what CHO would have to be, with no further hydrogens. Similarly, when you have CH3 and CH3s in the second example, both CH3s are easy. Now the CO in the middle, there are 2 ways you can interpret that. One is that just CO right next to each other, but you can see this carbon is missing a lot of things. It doesn't have any hydrogens on it. Apparently it shouldn't have lone pairs or more than 1 lone pair. So the actual way of drawing this is actually having CO double bond in the middle. CH3CO2H, if you just draw the atoms right next to each other in order, it would look like CH3COOH. Now oxygens are here are fine, okay, hydrogen are fine, but same thing, this carbon is not right. The correct way of drawing this is actually CH3OH is right, but CO in the middle will be CO double bond. So you can see with CO double bond, you allow this carbon to have a double bond and 2 single bonds in all 3 cases here. The last one is similar to the second last one, CH3 and CH3. So you have CH3 and CH3. In the center, you have a CO2. If you draw them in consecutive way, COO, the carbon will be missing bonds. The correct way is actually carbon with a CO double bond with 2 other bonds. I have to say, in the future, you don't really think this way. You just know that's what they are whenever you have a CO or possibly CO2. You can pause the video here to test yourself if you can convert A and B to complete the Kekule structure into condensed structure, or the bottom 2 condensed structure into Kekule structures. You can pause the video here, try it yourself first, or you can start replay the video. So the top one is going to be condensed structure is going to be, we're going to break them down to the groups. There's a CH3, there's a OH, and both bond to the CH. And then another CH double bond in the center, followed by another CH3 group. So here's how we're going to do it. CH3 bound to directly CH. Now this CH on the side, you'll have a OH. And CH is directly bound to CH double bond CH. And then next CH3. This is perfectly fine. Or if you want merge OH into the structure, it will look like this. CH3CH, OH parenthesis, to show that this OH actually is not in the sequence, but actually attached to the carbon in the front. followed by CH, double bond CH, and then followed by CH3. The second one will be, even though it looks more complicated, but as long as you follow the same pattern, break them down to groups, and you will be able to do it. So there are two CH3s attached to the CH. They are attached to the same CH. So this will be CH3 parenthesis 2 CH. The CH followed by CH2 and CH2s. So it will follow by CH2. You can draw another CH2, or you can put a parenthesis, 2 CH2s. And next, there's a carbon here actually, and this carbon is attached to the CH2 directly, so this carbon. But on this carbon, there are 3 CH3s, CH3 and CH3. So the way you draw this is going to be CH3 in parenthesis 3. Let me highlight the carbon that's a little bit different. The next example is actually expand this condensed structure into Kekule structure. Kekule structure of this will be, start with the bromine, which bond next to 3 CH2s. So it will bond to CH2 parenthesis 3, meaning this same units will repeat 3 times. Followed by a carbon-carbon triple bond. You should not be surprised that there's no other hydrogens attached to both these two carbons on the triple bond, as they both are completed with the full bonds already. The second carbon on the other side of the triple bond is bonded to a CH3, so this carbon is bonded to a CH3. Let me highlight the carbons I would like you to pay a little bit extra attention. The last one will be CH3 next to oxygen. And this oxygen is bonded to CH2. Not only one, there are 2 CH2s. And the last second CH2 is bonded to a CH3. Now on the oxygen in the middle, you can automatically add 2 lone pairs. So this is how you draw the Kekule structure and or the condensed structure. The actually most popular form of representing organic molecules in organic chemistry is actually called skeletal structures. The skeletal structures is further simplified from the Kekule structure. Here we're simplifying the structures by doing a few things. Number one is that we don't rejoin any carbons. The carbon atoms are going to be represented by the junctions of any 2 lines or at the end of any line. For example, in this case, hexane, you can see the backbone of the structure are 6 carbons. 1, 2, 3, 4, 5, 6. Now, without drawing all of the C's, we can simply use 5 dashed lines representing the junction point as the carbons in the Kekule structures. So that represents a carbon, that represents a carbon, and then also here, number 4, number 5, number 6. Now apparently, you would never try to convince people that when there's a straight line, there's a carbon in the middle. If you want to show there's a carbon there, you need to draw a band with showing the junction of the line. The other thing is, you don't draw the hydrogens. You would assume there are enough hydrogens around each carbon to make it tetravalent. So for example, in the hexane, you can see this zigzag line with 4 junctions and 2 terminal points representing 6 carbons. And on each carbon, there are different number of hydrogens. For example, the terminal carbon would have 3 hydrogens to complete 4 bonds. Other than the carbon-carbon bonds, there are 3 additional CH bonds. Now, assuming everybody acknowledges that, so there's no need to draw all the hydrogens. Similarly, for the junction carbons, or the carbon in the middle, which already have 2 carbon-carbon bonds, so here and here, you would only need 2 more hydrogens to complete the 4 bonds. So on this carbon, or this kind of carbons, there will be 2 hydrogens. So if you really want to complete the structure, it would look like this. On the terminal carbons, you will have 3 hydrogens. On the internal carbons, there will be only 2 hydrogens. Now, since this information are never going to change for this structure, so there's no need to show this kind of thing. It makes the drawings extremely clean to see how the molecule look like. Another example to the right will be the skeletal structure. It shows a hexagon shape, which is actually representing 6 carbons in the cyclic shape, and each carbon will have 2 hydrogens. There's only one thing we have to be ensured that we only emit the carbons and the hydrogens attached to the carbons. Any heteroatoms or the hydrogens attached to the heteroatoms has to be shown in the skeletal structure. They cannot be emitted. So for example, if you look at this structure, you can see there's a carbon, carbon, another carbon, but these 3 carbons are not exactly the same. The carbons on the terminals are actually CH3s, whereas the carbon in the middle only needs 1 hydrogen. The next carbon actually is a CH2. The next carbon is again another CH2. Chlorine has to be shown as Cl in the skeletal structure as well as the completed Kekule structure. This is a structure similar to this hexagon ring with 1 more carbon here. You can see all of the carbons on the ring are CH2s. The terminal carbon is actually CH3. Now this carbon in the middle is actually only a CH, with only 1 hydrogen needed to complete the 4 bonds. Now let's take a look at the multiple bonds. For example, triple bonds. So this is a 4 carbon chain. Because of the sp hybridization of the 2 carbons in the middle, so this has to be a linear geometry without zigzag shape. Now the terminal carbon are actually CH3s on both terminals, but 2 carbons in the middle are triple bonded. There are actually no hydrogens attached to these 2 carbons. When the carbon has a double bond, you have to be also carefully count how many hydrogens they actually have. So around this double bond, there are 2 carbons. The first carbon attached to additional 2 carbons, both are CH3s. So this carbon actually possesses 4 bonds already. It doesn't really have any more space to attach further hydrogens. Whereas the second carbon on the double bond, actually currently you can see there are 3 bonds. So there is 1 hidden hydrogen on this carbon. The next carbon, the carbon next to oxygen, is similar to the other carbons in the middle with 2 hydrogens, with the 2 bonds currently. Whereas this oxygen, you can see it actually has a carbon-oxygen bond, a hydrogen-oxygen bond with 2 lone pairs. You can see that even in the skeletal structure, this hydrogen has to be shown there. you cannot show this structure as this. Without the hydrogen next to the oxygen, it's wrong. Now, sometimes it could be a little bit challenging when there's a charge on the carbon. For example, a normal cyclohexane ring or cyclohexane shaped carbon-carbon structure would assume have two hydrogens on each carbon. But with what we have discussed about the charges on carbon, for example, there's actually positive charge on this carbon, then that means there's only one hydrogen attached to this carbon. This carbon has only 3 bonds with no other things attached to it. No other bonds, no other electrons. So this is a carbon with a positive 1 charge. If in the skeletal structure shows a cyclohexane ring with a negative charge next to a carbon, that means this carbon actually has 1 hydrogen attached to it, but it has another lone pair here as well. So this carbon has actually 5 associated electrons. So that's how it gets 1 negative charge. So difference you can see on both skeletal structures of structure above and below. There's nothing shown here except the positive and negative. The difference is that they both have 1 hydrogen, but the bottom one with an extra pair of electrons. Let's try a few drawings of going from the Kekule structure to skeleton structure, or going from condensed structure to skeleton structure. Skeletal structure are basically join the carbons and try to emit the hydrogens directly attached to the carbon. So make sure you count the carbons correctly first. There's 1, 2, 3, 4, 5 carbons with a double bond between number 3 and number 4. So make sure you start from 1 carbon, a dashed line, that's actually 2 carbons, 3, 4, 5. It doesn't really matter whether you go in backwards, as long as you draw 5 carbons. Now, you can confirm that by counting the carbons again. And then ensure that double bond or triple bonds anywhere along the carbon chain between number 3 and the number 4. And then attach other attachments onto the according carbons. For example, in this case, on number 2, there's an OH. And that's it for the first one. The next one will be, the major chain will be this. And you will find some other attachments or side chains on the main chain. The main chain is a 5 carbon chain again. 1, 2, 3, 4, 5. Now, on number, this is actually 6 carbon chain. I missed this carbon. So 1, 2, 3, 4, 5, 6. Now the attachment we're looking at here is on number 2, there's a CH3. On number 5, there are actually 2 CH3s. Of course, when you actually join the skeletal structure, you don't have to show the numbers. The numbers are just for your own reference. Number 3, you can see there's a bromine, and there are 1, 2, 3, 4, 5, 6 carbons. So there's a bromine, and bromine attached to 6 carbons. Now you have to be careful, even though we usually don't have the touch line with the bromine, but you have to recognize this is not a carbon. The actual first carbon starts from here, and there's a carbon-bromine bonds. And second carbon, 3, 4, 5. You need 6 carbons, so you need to draw one more. Once you complete the main train, carbon train, the rest of attaching to side trains will be relatively easier. Just look at the original structure. Between number 4, there's no actual side attachment. Between number 4 and number 5, there's actually triple bond. So 1, 2, 3, 4, 5, 6. There's actually triple bond. Now, realizing that number 4 and number 5 are sp hybridization with triple bonds, we need to make them more linear looking. So let's redraw the tail part. So number 3, number 4, number 5, number 6. So this is number 2, 1, 2, 3, 4, 5, 6 carbon. All right, the last one. There's a CH3, which is a carbon, attached to an oxygen. Now, in order to show a CH3 attached to an oxygen, this is how you show it. This is a CH3, which you don't have to show anything, and then attached to an oxygen. And this oxygen is further to attach to CH2, parenthesis 2, meaning this CH2 repeats. There's a CH2, another CH2. The CH2 attached to another CH3. So CH3, which is this carbon, CH2s are these 2 carbons, and CH3 will be the last terminal carbons. Now, one of the common mistake is that there's no, next to oxygen, the dot here, it doesn't mean anything. It's just a bond attached to the oxygen. It doesn't mean any carbons.